East, and welcome to Scopes University. In this episode, we're going to learn how eye diagrams can be used to identify noise and jitter in your signal that can ultimately cause errors in the data that you transmit. I'm actually going to discuss this topic in two parts. So in this first episode, we're going to learn the basics of what makes up an eye diagram, why you want to use one to analyze your clock signal and your serial data, and then how to quickly set one up on the scope. In the next InfiniVision episode, we'll analyze that eye diagram even further by performing jitter measurements on it to figure out how we can eliminate any errors or anomalies that we're seeing. Eye diagrams are helpful in testing the physical layer fidelity of clock signals and serial data. So what it is a layered view of each of the different bit transition combinations, and there are 8 of those in total. So this provides a composite picture of the overall quality of the physical characteristics, like amplitude variations, timing uncertainties, and infrequent glitches. The first thing we need to do before we set up the eye diagram is take a bit rate measurement. So the bit rate is basically just the pulse width of each of the bits. So you can see the signal I'm working with on screen here is serial data with a lot of jitter riding on it. And to figure out what the bit rate of this signal is, I want to stop the acquisition. Then I want to zoom out and find one of the smallest pulses I can see in this signal and center that on screen. Now I can go into my measurements menu and add a measurement. We're going to add a bitrate measurement. Now I can see a rough estimate of what my ideal bitrate should be, around 6.2 megabits per second. Now that we have this measurement, we're ready to get started with our eye diagram. But my first question when I was learning about eye diagrams was, how do you get it to look like this with all of the bit transitions layered on top of each other like that? A normal trigger couldn't do that. And the answer was clock recovery. So some signals use an explicit clock, which just can be driven right into one of the channels of the scope. But other signals use an embedded clock. With an embedded clock, you have to have some way to de-embed or recover it. So that's when you use clock recovery. So what the clock recovery actually does is calculate the exact ideal bit rate of the signal that you're working with. So let's take a look at some of the different clock recovery options that we have to work with. So the first thing I want to do is turn off my measurements and press auto scale. And then we can go into the analyze menu. And in here we're going to go to features and select real-time eye, but we don't want to turn it on yet, so we only want to select it once. Then we'll go into the clock recovery menu. And in here we can see the different data rate options that we have. So there's fully automatic, which you would want to use in the case that you have no idea what the bit rate of the signal that you're working with is, and you want the scope to completely calculate that exact ideal bit rate for you. Semi-automatic should be used when you have an estimate of what that bit rate is, and you want the scope to use that estimate to figure out what the ideal bit rate should be. Manual is used when you know that exact ideal bit rate that you want to work with. So since we have a rough estimate of what the bit rate of the signal is, we want to use the semi-automatic option. So the scope will use that bit rate that we found in order to calculate the exact ideal bit rate of the signal. So in the nominal data rate box, we want to plug in that 6.2 megabit bit rate that we just measured. And we can also see there are a few different methods of clock recovery as well. So there's constant frequency, first order and second order PLL, and explicit. So again, an explicit clock is when you have that clock signal that you're actually able to plug into one of the channels. Constant frequency is what you use when you're working with an embedded clock. And we'll talk about the first and second order PLLs in the next video. So let's leave it at constant frequency and select OK. And now all we have to do to set up the eye diagram is select Auto Setup. And that's going to automatically set up the eye diagram in the center of the screen. So the scope will set up that eye diagram centered around that ideal bit rate that it calculated. And it uses color grading to display this information. So if we go into the color grade menu and select show color key, we're able to see just how frequent or infrequent the signal is coming through certain areas of the screen. So this will allow you to see if your signal is flipping bits correctly or if there are any delays or jitter. Having jitter or glitches in your signal can be bad because that means when the data is transmitted, it can be interpreted wrong on the receiving end because the bits aren't coming in correctly. So you're actually going to be getting the wrong data on the receiving end. Notice when we opened up the eye diagram, we got 2 custom measurements that popped up in the sidebar, the eye height and the eye width. So this shows you the largest amplitude and the widest opening of the eye, and you can verify and compare that with your specifications for the signal and debug if you aren't seeing what you expected to. And we can take a look at the statistics of those in the measurements menu by turning on the statistics display and we can see the mean of those measurements. So this is going to give us a better understanding of what's happening on average in this signal. And we can learn more information from this eye by really quickly bringing up a histogram. To do that, we just draw a box on the screen and select histogram. So what does this histogram actually mean? Well, you'll have to find out in the next episode. So we just learned some of the basics of what makes up an eye diagram, why you want to use one to test your signal, and how to set it up on the scope. In the next InfiniVision episode, we'll be doing an even deeper analysis of this eye diagram using the jitter measurements to figure out what might be causing the anomalies that we're seeing in this signal. Thank you for joining me. If you want to learn a little bit more about eye diagrams and how to do mask testing with them, make sure you check out the application note, Can Eye Diagram Mask Testing? Follow us on Instagram, Facebook, and Twitter, and make sure you subscribe to our YouTube channel so you can see more videos like this.